This is the first of two lectures which give an overview of the processing of seismic reflection data. In the previous two lectures we've seen how the seismic energy travels through the Earth, how it is reflected from the interfaces between different types of rocks, and how these reflection events and many other kind of events are recorded on the seismic traces. In this lecture and the following lecture we'll look at how those seismic traces are processed to produce a seismic cross-section type of display which gives a representation of the geologic structures in the Earth below the line of seismic data. Now, the idea then of data processing, or perhaps I should say the main idea of seismic data processing, is to produce the seismic section which is a pictorial representation of the geologic structures below the seismic line. And for the purposes of these lectures we can divide the processes that are used into two main groups: what I've called geometric processes, which are concerned with making corrections to the data for certain aspects of the recording geometry, that is, the way that the seismic source and receivers are arranged on the surface for the seismic data collection. The other group of processes are the signal enhancement processes, which are mainly concerned with removing the unwanted reflection events and other events such as noise from the seismic data to give a clearer picture of the primary reflections on the data. The geometric corrections that we'll look at in this lecture then are just four of them: the normal move-out corrections and static corrections, a process called common depth point stacking, and finally, although it's not used always on data, a process called migration. Now, in order to understand how these processes correct for the geometry of the recording system, we first of all have to look at the typical methods that are used in collecting the seismic data. The usual system for laying out the source and receivers in what is called a recording spread is to have a series of receivers or interconnected groups of receivers laid out at regular intervals along the surface, and to have the seismic source off one end of that line of receivers. Now, almost all the marine data that is collected is recorded with this type of system, and a certain amount of the land data, although on land sometimes another line of receivers is laid off on the other side of the shot to give what is called a split recording spread, so that the source is in the center of the line of receivers. But that's really just like two of this type of spread laid back to back. This type of recording spread with the source off the end of the line of receivers is called an off-end spread. Now, if we have some reflectors in the Earth below this spread, we'd get a series of ray paths, such as some that are illustrated here, from the source to the reflectors and back to the receivers. Now, one point you will notice is that if we have a line of receivers of some length, such as drawn here, if you look at the geometry of the ray paths, you'll see that the distance covered by the line of reflection points on the reflector is going to be half of the distance covered by the line of receivers on the surface. And this distance covered by the reflection points for this spread of receivers is called the subsurface coverage of that line of receivers. And you'll note that that subsurface coverage is that same half spread length for any reflector in the subsurface because of the geometry of the reflection paths. Now, in this particular example, we've just taken a very simple case with 6 receivers in the spread, but in practice it's more usual to use, or maybe 48 or 96 receivers are the most commonly used types of spread, although on land as many as 1,024 have been used in one recording spread. Well, if we look at the type of record that is obtained from a spread of receivers such as this from one shot of the seismic source, the 6 traces would look something like this. The direct arrival energy traveling along the surface would form a straight line across the set of traces. Because the receiver groups are laid out at equal distance increments, it would take the same amount of time to travel from receiver to receiver, and therefore those direct arrivals form a straight line across the record. The reflection events form curves across the record, and that is because, fairly obviously, the travel path from the source to a reflector to the near receiver is much shorter than it is from the source to reflector to one of the more distant receivers. Therefore, the reflection obviously arrives later at the more distant receivers, and the geometry is such that the reflection event actually follows a curve across the set of traces on the record from these receivers. A deeper reflector would form a curve also, but it would be less curved than the shallower reflectors. Well, this then is the way in which seismic data is usually recorded with a fairly large number of receivers recording traces from each shot of the source. When one record has been made with this type of arrangement, then the whole setup of sources and receivers would be moved along the seismic line some distance, and the process would be repeated. The distance which the source and receivers would be moved is usually some increment of the spacing of the receiver groups. Well, we can look at that in a little more detail on this drawing, where we're showing a source and 6 receivers for one firing of the source, and then the source and the 6 receivers again after they've been moved along the seismic line for the next shot, and then once again for a 3rd shot. The 3 situations are drawn separately for clarity, but one common receiver position on the surface would be in vertical alignment here. So that receiver, that one, the 2nd one on this spread, and the 3rd one on that spread would be occupying the same place on the surface, but for successive shots. So from this type of recording method then, we would obtain subsurface coverages, as indicated here, of half a spread length from that shot, then from that, and from that. You'll notice that those subsurface coverages overlap because the distance that the recording spread and source have been moved along is less than the length of the subsurface coverage. Now, this gives what is often called multiple coverage data, in that we are obtaining multiple subsurface coverage on each reflector. Now, when the data is recorded, all the traces from one firing of the source from S1 would be on one record. The traces recorded from this setup would be on the next record, and from this setup would be on the next record. However, once the data is read into a computer for processing, it's relatively easy to reorder these traces into different groupings, to gather them up into different sets. And this is generally done at a certain stage in the processing. And we would gather the traces into what are called common depth point sets. Now you'll notice that one of the ray paths drawn here in a heavier line is reflected from a certain point in the subsurface. On the next shot, that ray path, which has the same reflection point on the subsurface, is again drawn in a heavier line, and once again on the third shot. So here we have three traces with different travel paths with regard to the source to receiver distance, but all of which are reflected from the same point in the subsurface. Now, when we gather the traces into common depth point sets, we are gathering sets of traces such as these three, whose common characteristic is that they have the same reflection point on any particular reflector. So if we collect those three traces together then and look at their travel paths separately from all the others, they would form a set of travel paths like this. From separate shots, 1, 2, and 3, and they go to different receivers and different receiver positions. Another common feature of this set of traces is that the source and receiver for each trace is centered on the same point, what is called a common midpoint for this set of traces. And in fact, this is really the characteristic which defines what are often called common depth point traces. Strictly speaking, they are common midpoint traces in that each trace has its source and receiver centered on the same point. Now, in most situations, this also means that they have common reflection points on each reflector, but not in every situation. They may be slightly different. So remember that the real definition of a set of common depth point traces is really their common midpoint characteristic. Well, as we'll show later, the traces are arranged in these types of records, common source records they're sometimes called, because all the traces are recorded from a common source position. They're recorded that way to begin with, and certain processes are applied to them in that form. But then the traces are regathered into common depth point sets at some point in the processing sequence, so that other processes can be performed on them in this type of arrangement. Now, if we look in a little more detail at a set of common depth point traces, and here we've shown what would be called a six-fold common depth point set of traces, because there are 6 traces from 6 different source positions into 6 different receiver positions. If we look at the traces that would be derived from those different receivers and arrange them in order of offset, that is the distance between the source and the receiver, a reflection event, and remember this would be from the same point on the reflector, would appear along a curve across this set of traces. Now, as we mentioned before, usually the arrangement of sources and receivers is such that the spacing between these receivers in a common depth point set and between the sources would be an equal increment. So in other words, the offset increment between these traces would be constant. However, as on the original field records, a reflector forms a curve across the set of common depth point traces. That curve, in fact, is a hyperbola. Now, one particular characteristic of this hyperbolic curve on a set of common depth point traces, which is different than it is on the original field record, is that for a particular reflector, that curve does not depend on the dip of the reflecting interface in the Earth. In other words, if we had a situation such as this, where the reflector is not horizontal but it is dipping to some extent, so that our set of common midpoint traces, as they really are, would in fact still be reflected from almost the same point on the reflector. The reflection points would be close enough that we can consider it a common reflection or depth point. The curve of that reflection across the set of common depth point traces would be no different than would be obtained from a flat reflector which arrived at the same time on the near trace. However, on the original field records, in the situation with a dipping reflector such as this, although the reflection event would again form a curve, a hyperbolic curve across the set of traces, it would be a different curve, in fact less curved in this case, than for a reflector with the same velocity of travel to the reflector that arrived at the same time on the near trace. If the dip of the reflector was in the opposite direction, in other words, if it dipped down in this direction, then the curve across these traces would in fact be greater than for a horizontal reflector. So this is one important characteristic of a set of common depth point traces, that the curvature of a reflection across them does not depend on the dip of that reflector in the Earth. Now we'll look in a little more detail at the curvature of the reflection events, and this applies particularly to the primary reflections, but also to the multiple reflections. We'll look at the curvature of those reflections across a set of common depth point traces. Now, we're looking here at just one particular ray path out of a set of common depth point traces, from the source to the reflection point and back to the receiver. Now, the source and receiver are equally spaced on either side of the common midpoint for this set of CDP traces. So if we say the source receiver distance is x, then the distance to the midpoint is x over 2. And also we'll assume that the velocity for velocity of travel for the seismic waves from the surface to this reflector is v. And we'll define the travel times from source to reflection point to receiver as Tx. And we also imagine that we had a source and receiver placed both at the common midpoint, so that we have a trace which travels from the midpoint, which has a travel path rather, from the midpoint to the reflection point and back to the midpoint again. And this is sometimes called a zero offset trace because we're imagining zero offset between the source and receiver. And we'll say that that travel path leads to a travel time T0. Now, if we take one of the triangles in this travel path, then by Pythagoras' theorem, the square of the hypotenuse is equal to the sum of the squares on the other two sides. And that leads us to this equation here, where the distance along one of these sides, along SC, for instance, is the velocity multiplied by half the travel time along that travel path. Anyway, that leads to this equation, which simplifies down to this. It's an equation relating travel times for the real trace and for the imaginary trace to the distance between the source and receiver for this trace and the velocity with which the seismic energy travels to that reflector and back. Now, the important point at this stage in the lecture series is not the details of the mathematics, but simply to remember that there is a relationship between travel time, distance between source and receiver, and velocity of travel for a particular seismic trace. Now, this gives us, in fact, a way of determining the velocity of travel of the seismic energy from the reflections themselves on the traces. If we have two traces or more which are from a common depth point set, it is possible from the reflection travel times on those two traces and knowing the offsets from source to receivers on those traces, which of course we do know, it's possible to, in effect, turn this equation around and derive the velocity with which the seismic energy traveled. And of course, that velocity is needed in order to convert the travel times we measure from the seismic data into depths to the reflectors. Well, looking at this question of reflection curvature on a set of common depth point traces now, rather than just one trace, the curve is sometimes referred to as the normal move-out curve. But normal move-out is actually a measure of a certain time on the traces as it's defined here. Now, we're imagining a set of 6 common depth point traces and also the zero offset trace, which is a kind of imaginary trace because we don't normally have a source and receiver coincident at the midpoint. Now, we've seen that the travel times and offsets and velocities are related by this equation. And now we'll define a quantity called delta t, delta time, as the difference between the travel times on a trace at some offset and that on the zero offset trace. So in other words, if we have a reflection arriving at this time on a trace at some offset x, and a reflection from that same point arrives at this time on a zero offset trace, delta t is the difference between those two times, between the zero offset travel time and the actual travel time on a trace at a particular offset. So that is the definition of normal move-out. That delta t is often referred to as the normal move-out of this reflection. And of course it relates to a specific offset from the source to receiver. Well, if we make this substitution, we can derive this equation which relates normal move-out to offset and velocity and zero offset travel time. Once again, the important point to note is that there is this relationship between travel times, offset, and velocity, which eventually allow us to determine velocity from the travel times on a set of traces such as this. Now, one other feature of normal move-out, this curvature of the reflections, is that on any particular trace, the move-out of the successive primary reflection events on that trace will always decrease. So in other words, the curvature on the primary reflections always gets less at later times on the record, which alternatively means that the normal move-out is decreasing with time. having seen what normal move-out is and how it arises on the seismic records, it's an effect due to the fact that we have different distances between the source and receivers for the various traces that we record. And one of the first geometric corrections that has to be applied to the seismic records is to correct for the differences in travel time of the reflectors caused by these different offsets. Now, this normal move-out correction, or NMO correction as it's often abbreviated to, is applied to each set of common depth point traces. So before normal move-out, the common depth point traces would look like this, with each primary reflector showing a certain move-out curve across them. The move-out correction simply consists of applying time shifts to the data, to the reflections on the traces, to shift all the reflections to the times that they have or would have on a zero offset trace. So the data on a set of CDP traces looks like this before normal move-out correction. After move-out correction, the reflections look like this. They're all aligned at the time they would have on a zero offset trace if we'd recorded such a trace. Now, normal move-out correction would correct the reflection events to same times on each trace as I've shown in the previous slide if the sources and receivers were on a flat surface. Now, in marine data collection, the situation is like that because the sea surface is, of course, horizontal. But on land data collection, we're generally working on an irregular surface, so that the Earth's surface would show some elevation changes, and of course our sources and receivers are either on that surface or just below it in the case of the sources. A set of common depth point ray paths then for a series of sources and receivers with a common midpoint on this surface would look something like this. If we took those traces and applied normal move-out correction to them to correct for the different offsets of the traces, the data afterwards would look like this. The reflections are not all at the same time on the set of common depth point traces, even though we've applied normal move-out correction. The differences in arrival time of the reflections are caused by the different elevations, and also, in most cases, by the fact that there is usually a layer of very low velocity material, weathered material, just below the surface. So these remaining time differences on the reflector are due to different elevations. Obviously, it's going to take a somewhat longer travel time to a higher elevation, or from a higher elevation, than it would from a lower elevation. And also, there'll be different travel times through this very low velocity material. So we have a situation then where normal move-out doesn't correct all the reflections to the same time on each trace. Well, the way in which that is corrected is illustrated on this slide. We pick on a certain elevation, usually called the datum plane or datum elevation, and generally it's chosen so that it's somewhat below the base of this low velocity weathered layer. We arbitrarily pick this certain elevation then, and by a series of analyses we can determine the velocity of this near surface layer, and we would measure the elevations of the sources and receivers on the surface. And so it's possible to calculate the travel time from each source down to this datum plane for each travel path, and also the travel time from the datum plane to the receiver on each travel path. So we can then, after calculating those travel times, we can subtract them from the appropriate traces. for each trace which subtract a travel time at the source end of the ray path and a travel time at the receiver end of the ray path. And after doing that, and also applying normal move-out correction, a set of common depth point traces would, again, show each primary reflection aligned at the same time on that set of traces. And that time would be the time for a zero offset trace from this datum elevation. It's as though we had moved the sources and receivers from the surface where they actually are down to this horizontal datum plane, and then measured all the travel times from there to the reflectors. Now these corrections are called static corrections. The reason for that is that the amount of time correction we apply is the same for any reflector in the subsurface, because it would undergo almost identical travel paths through the near surface. So since these time corrections are just constant time shifts of each individual trace, they're called static corrections. This is in contrast to the normal move-out corrections, where we have to correct for different normal move-outs down the trace, and therefore the normal move-out correction is a time shift which varies with record time, and for that reason it's often called a dynamic correction. Now the purpose of applying normal move-out corrections and static corrections to the sets of common depth point traces in order to get all the primary reflection events at the same time across that set of traces is to enable a process called common depth point stacking to be done. So we've started off with a set of common depth point traces with a series of different travel paths, such as this, from the surface to a reflector, which would give us a series of traces looking perhaps something like this, with the reflection event falling approximately on a curve, along a normal move-out curve, but each individual reflection perhaps being slightly off that curve because of the static effects. When we apply NMO and statics, we correct that, or each particular primary reflection, to its zero offset time on each of the set of CDP traces. Common depth point stacking then consists of summing those traces together to form a single trace. Now when we sum the traces together, it simply means that we take the amplitude on each of these traces at the same time and just add all those amplitudes together, and that is the amplitude on the output trace. So for instance, if these reflections are perfectly aligned, the peak amplitude on this reflection would be at the same time on each trace, so we just add all those peak amplitudes together and come out obviously with a much larger peak amplitude on the summed or stacked trace, as it's usually called. Now in doing this, if we consider the ray path situation, what we've really done is take a set of traces with different ray paths, although they have a common reflection point, and corrected each of them to the travel times that we would have if all the ray paths were from the common midpoint on the datum plane to each particular reflector and back. So this set of traces all have primary reflection travel times that would occur if they all had this travel path. Since they have in effect identical travel path times, we can then sum them together and derive a single trace representing the primary reflection times for this type of zero offset travel path. So once again, we've really converted from a series of different ray paths in effect to a single ray path like this. So we've simplified the situation and of course reduced the number of traces by some fairly large factor. There might often be 48 or 96 traces to be summed together in each common depth point, so it can be a very large reduction in traces. This in itself leads to some economy in processing just by reducing the number of traces, but common depth point stacking also has a lot of other beneficial effects which will be explained later. Well, we've looked at what occurs to each individual set of common depth point traces in common depth point stacking. Now if we look at a sequence of common depth point traces along the seismic line, we started off with a situation where each individual record as it was made in the field had a whole variety of travel paths on it to the different reflectors, and we've, by the process of move-out correction, static correction and common depth point stacking, we've in effect simplified the ray path picture to this, where all ray paths start from a series of equally spaced points on some datum plane. So that those traces, if we displayed them, as we do, in the form of what is called a stacked section, would show reflection times such as these from two reflectors such as this, a flat one and a dipping one. So that the reflections on the stacked traces, on the stacked section, form a kind of picture of the geologic structures, the attitude of the various reflectors below this seismic line. So that is one of the main purposes of processing the seismic data, is to obtain this pictorial representation on the stacked section of the structures below the seismic line. Now, sometimes, if some of those reflectors have relatively steep dips, the picture of them that we obtain from the stacked section is somewhat distorted because the reflectors are not in their correct position relative to the trace origins on the surface. And the reason for that is illustrated here. If we have some dipping reflector which has a certain finite length from x to y, then the zero offset ray paths from a series of points on the surface to that reflector would look like this. So in fact we would see reflections from this reflector at a series of stacked trace positions from A to B, when in fact the reflector lies vertically below the points C to D on the surface. However, when we display the traces, the stacked traces that in effect have these travel paths, the traces are displayed vertically below points A to D. Therefore the reflector, the dipping reflector, appears to lie below the positions A to B on the stacked section, when in fact it laid between C and D. Now migration is the process which is used to correct this misplacement, if you like, of the dipping reflectors. It's a process which takes the stacked section, and from the dips of the reflectors it calculates the amounts of shift laterally that must be applied to those reflectors to put them in the right position. So in this case, when we apply migration, it would shift this reflector across the seismic section and position it from below point C to point D on the surface, just as it should be. In the process, you might note that it also tends to shorten this reflector somewhat. This is another aspect of recording a dipping reflector, that it tends to appear longer on the stacked section than it really is. So these are the main processes then that are used to geometrically correct the seismic data as we record it to produce a stacked seismic section which is a pictorial representation of the geologic structures in the earth below the seismic line.